In this lecture, we're going to talk about particle filtering. Particle filtering is the second idea under linearization or uncertainty propagation methods that we explored. In particular, we're talking about a class of nonlinear processes and measurement models. Together, they form a nonlinear systems. These systems are ubiquitous. They're everywhere. It's not basically studied in isolation. This is typically the real problem we deal with. They are not linear. They're complicated systems. You could, to help your imagination, you can imagine an autonomous flying taxi. It's a very complicated system. Now, maybe you're modeling just the motion of this vehicle, and then that forms this nonlinear system. But you could have multiple such nonlinear systems to model different aspects of this vehicle, right? Or now, autonomous racing cars are becoming popular. And so there are many examples of them. So in general, we discussed about multiplicative noise, additive noise, because it was important in the context of Kalman filtering. It would make calculation easier if the noise was additive. But here, typically, we talk about a general class of nonlinear systems with noise, the most general case, which is multiplicative noise, okay? So again, our motivation here, what was our motivation? We're going to talk about the technicalities and what to do basically for solving certain problems. But our motivation was that given a system and certain models, we wanted to solve some state estimation tasks, right? These tasks could be tracking, localization, some sort of perception tasks. Maybe it's coupled with planning and navigation. So altogether, that was our motivation. So this is the third method we're going to learn. To answer this central question that if I have a probability distribution, given that there is no perfect actuator and sensors in reality, and I have to deal with distributions and uncertainties, if I have a belief over my quantity of interest, and I need to send this belief recursively every time through that nonlinear model, how can I do that? In general, there is no exact formula, unlike the linear case. So we came up with two ideas. We talked about linearization and analytical methods using Taylor expansion that led to the extended Kalman filtering. There was another idea. It was derivative-free. It was based on deterministic sampling, and that led to the unscented Kalman filter. So we learned already two methods for nonlinear state estimation. Today, we are going to talk about a third idea. This third one is based on the idea of random sampling. If we can generate random numbers in a computer, and we can create many hypotheses to simulate the evolution, or many hypotheses that can a probability distribution basically evolve to over time, then maybe we can track multiple hypotheses and then find out which one is more likely as we roll out and obtain more observations. That's basically the idea, okay? So the concept is very intuitive and simple. We use a computer to simulate, track the evolution of the posterior, and use the measurements to weight them and then see which one will be likely. There won't be one of them. There's usually multiple of them. But at least we can track them with certain weights. That's basically the idea. And the math is really just to back up and make sure everything will be in place. It won't fall apart. It will converge to something correct, right? So the general idea that is very old, from 50s and 60s, when we had computers and we could draw random samples. Samples are examples, right? These are different examples that in this context we call them particles, right? So each particle is an example or hypothesis. So Monte Carlo methods is a bigger class of basically techniques. They're all based on random sampling and simulation. I shared some background with you. It's good to discuss it outside of lecture, but it will eat the lecture time, and we won't be able to talk about the robotics aspects of it as much as we want. But that's Monte Carlo integration. I have an integral. I want to approximate it. We can use Monte Carlo, which is based on random sampling. It's fun to implement. These algorithms are typically easier to implement than the previous classes of problems that were somewhat less digestible because you have algebra. You need to be careful about the derivations and not making any mistakes. So in general, they are easier to implement. Another nice properties of this class of problem is that it can deal with, we'll see, nonlinear posterior, multimodal posteriors. So more complicated. Kalman filter was tracking a Gaussian distribution for us. We were very limited in the type of posterior that we're trying to estimate, okay? So the Monte Carlo methods are basically simulation-based method. However, we're going to talk about a more special case of Monte Carlo methods, namely sequential Monte Carlo methods, SMC. Because the data that we have arrive sequentially in time, right? And we want to process it recursively. We're still in that framework of Bayes filter. Although this method can be more general, and I'll point out when we reduce it to filtering in today's lecture. So this is the context. We're covering a third idea, which is not from the same family of methods. It's no longer basically an algebraic filter like a Kalman filter. So observations arrive sequentially. That's important for us. That's what the sequential aspects of this method will enable us to implement it in real time on a robot. Otherwise, it will be offline. You have data, and you maybe run your simulation to infer some interesting value or quantity that you want that won't correspond to real-time, basically, algorithms. We can deal with non-Gaussian, high dimensionality, and nonlinearity, okay? Now, when you see these features in a problem, then you might want to start thinking about this method. Because as soon as you read non-Gaussian, well, you might want to look into the problem and see how non-Gaussian. A little skewed, maybe it's okay, right? If you're lucky enough to have access to some data and see the behavior of the system, if it's really multimodal, it's at one point in one place in the state space, another point is just completely in a different space, there's just jumping behavior, then maybe a Kalman filter might not be the best choice for tracking because it will not be able to deal with this change of mode in the behavior. Can it happen in robotics? Yes, that's a very common problem. So it's called kidnapped robot problem. We used to have this, I think we still have it, this RoboCop challenge. Robots would play soccer in teams, right? Or it's just a robot exploring. And then you come and lift the robot and put it somewhere else. For any reason, the robot is lost, or maybe you just want to reinitialize it. But the poor robot has no idea you did that. So it's trying to track The robot thinks it's here. You move the robot to the other side of the room. It might never happen, or it might take a very long time that the robot can recover from a sequence of observation what just happened. That's the kidnapped robot problem. So particle filters, because they can track multiple hypotheses, it's more likely a particle filter can recognize that and basically shift the mass of the estimate to not a more likely hypothesis, which might be the other side of the room. Okay? So basically, when analytical solution is not possible and you're dealing with a highly nonlinear multimodal systems, you might want to think about particle filtering. There's a price to pay, obviously. It cannot be just gain, but we'll talk about it later. Now, to avoid a misconception, although it's called particle filtering, now you know filter is a technical term we use. It can be used both for smoothing and filtering.
I had a question about the slide before this.
Huh?
So the second point that's made there about the posterior distribution being updated as data becomes available. So this is where, say you have a robot where your sampling rate from your measurements aren't as frequent as maybe how frequently you like propagate your dynamics. So you're not getting data as frequently as you're moving. How does this deal with the instance where you have like gaps in your measurement between?
Let me see if I understand the question. You're asking if because we want to run this filter as data becomes available recursively. I think your question is that what if data that I'm receiving is not that frequent? What will happen? My answer is that that's not basically a problem of this method, because it can happen to all the other methods too. If you do not have data or observations, you cannot basically correct your belief. So you have two options. You either need to resort to assumptions, right? Model is some sort of assumptions because it's imperfect. You're assuming that's the behavior, right? It might be a good model. It can be a good assumption, right? That means it works well in practice. Or you need observations, and ideally you need both, which we use both of them in Bayes filtering, right? Now, if you don't have observations, you're continuing with assumptions, models, to propagate for a long time, you might expect at some point, sooner or later, the filter will become degenerate. But the amount of information that it's giving you is so low that it's not useful anymore, okay? So that, we assume we have a sequence of data, observations. And that's usually, in practice, not a problem because imagine a robot or autonomous systems. You have a variety of sensors. If the sensors are proprioceptive, like IMU encoders, right? Some signals that are not perceptual measurements from the environment, you always have a continuous stream of them at a very high frequency. Can be kilohertz, right? Unless the sensor fails, you will have the signal. If it's perceptual data, for example, cameras, LiDAR, radar, they come at a lower frequency, but they have higher bandwidth. So the spatial sensors, a point cloud from LiDAR can have 100,000 points, or a stereo camera can give you 300,000 points. And they come at maybe 10 hertz, 30 hertz, maybe 60 hertz, but it would never be kilohertz at this point, at least. So it's often the case that we have more data to process than we can. So you might drop frames, you might do downsampling, and all sort of hacks to get some sort of observation that you can actually process within available time budget, right? So your concern is valid, and it's very important conceptually, but in practice, the challenge is, at this point, the challenge is often the opposite. You have more data to deal with, okay? which motivated, that's a good question, because that motivated a lot of people to work on dedicated sensors with internal chips, for example, to maybe a camera should have a processor to do certain image processing, like edge detection, maybe segmentation. Because if you want to do all of them on the perception computer of the robot, we just can't handle the amount of computations that it takes, right? So future sensors might become smarter and smarter, smart sensors. Or you sell a robot that maybe comes with this localization built in, right? So it can be used for both filtering and smoothing. Is anybody here remembering what was the difference? The difference between filtering and smoothing.
Filtering is used on time t, the data up to time t to infer time t data. And smoothing is used on sequentially data after time t to infer time t.
Yes. So the filtering uses the data up to current time, whether we make certain assumptions like Markov or not. It uses data up to now to estimate the state at the current time step. Not the history, not the past, not the future, right? The smoothing approach, it tries to estimate the entire trajectory. Use all the data to estimate the entire history up to now. In a sense, we can use data in the future to correct the past estimates, right? It can be done offline, can be batch. You can do it. The question came up on Piazza, can we do it in a sliding window? Yes, that's perfectly fine. You can have a fixed lag, a smoother. It's a sliding window moving in time. Not the entire history, but maybe 10 seconds instead of just the current step, right? So that's the difference. And then we had prediction, right? Prediction was about making inference or predicting a value in the future based on all you know right now. Okay, some background. We will need this delta function today. So you might remember it from one of your physics courses or some courses in math that we talked about Kronecker delta. That's a discrete version of delta function. The Dirac delta function is a continuous version. It has a very strange definition that around a certain point is infinity, and then 0 everywhere else. And then by definition, when you integrate this function, it gives you 1, right? Now, of course, it doesn't make sense to integrate infinity, but that's just the definition of the delta function, okay? So you can think about it as basically, if it's centered around A, it doesn't have to be 0. So the infinite mass just centered at 1 point, right? Basically, that's what it's saying. Now, if you think about it as a probability measure, then you can think about it as a mass function that you're just centering all the probability mass at one location, okay? That concept is important for us for the approximation that we will make soon. Now, one interesting property of delta function is that it breaks the integral. That means if you multiply it by a function and then take the integral, because it's 0 everywhere else, right? It ends up, the summation, it ends up being just the evaluation of your function at that particular point, A. It's also called evaluation functional in analysis. So it can evaluate your function at a point. Or you could think about this as some sort of expectation, right? If your density is delta, you're taking expectation with respect to delta, it just evaluates your variable function or whatever it is, okay? Okay, so this is what we need to talk about a perfect Monte Carlo sampling. What I mean is, if you want to have an ideal case, right? If we could have anything we wanted, what would be the framework? This is the framework that we're going to talk about it. Perfect Monte Carlo sampling. So it's important to understand the ideal case, and then we see what's missing. And then we will see if we can come up with an idea to compensate for the missing part. Okay? That's our approach here. Now, suppose you know the posterior. It's given to you, right? And we can draw samples, IID samples. So IID samples are independently and identically distributed, meaning the samples are independent, right? You don't use one to draw the other one. They are independent events. They have the same distribution, identically distributed. They have the same, they come from the same distribution that has the same mean and variance, right? So we call them IID. So when you hear particles, it's the same thing as examples, hypothesis, random samples, right? You can put it in a set. Now, notation is a little complicated, but you remember time steps were like this, right? This was basically a set of x0, x1, all the way to xk. For each particle, we're using some index as a superscript, okay? So we have n of them, right? This set here, it's basically, it's a compact way to write n examples. When I write, let's say y, I, it doesn't matter, basically subscript or superscript, I equals 1 to n. This means y1, yn, okay? It takes less space if you write it like that. So we have, imagine you have the posterior. You can draw n IID particles, random samples. We can define an empirical estimate of this distribution using delta masses placed at every IID example, right? So if you, this is just a notation to emphasize that the mass of the probability is placed around these IID samples. So if the probability is placed around these samples, the total mass is just some of them, okay? Because delta is giving you, in terms of a probability mass, we integrate, right? It gives you 1. When you have n of them, you need to divide it by n, right? Because this will be n over n equals 1. As a discrete probability, right? Does that make sense? Everybody is following? I'm going to draw an example to make sure we have an understanding of the starting point. Imagine we have a complicated posterior distribution. We know it. We draw, not only we know it, and we can draw random samples from it, right? Imagine you draw random numbers and well, around the modes, you should get more, right? That's how it works, because the density, the PDF, is assigning a relative, basically, likelihood or value to each event. when the peak is higher, that means it's more likely that that happens. Just like when it's Gaussian, you get more samples wherever the mass is concentrated. So to make sure that notion is respected, we should get something like this. Now, place an equal mass, right, on each of these examples. We have n of them. What is the probability of each sample? 1 over n, right? And this delta notation is telling me where they're located. Don't worry too much about the notation, right? So delta is telling you where it's located, following that idea that delta of x minus a means it's centered on a. So the mass is centered around these samples. If you weight them equally, y equally, because they're IID, right? We have independent events. We don't have any preference over one or the other. Let's just weight them equally. 1 over n, we have n of them. That will add up to 1. That's our probability mass function, approximated using essentially a set of independent events. So to summarize, if you know the posterior, if you can draw samples, you can do this approximation. That's not a problem, okay? Why we do this? Well, because even if you know the true posterior, taking the expectation of a function to calculate an integral like this, right? It might not be easy because in general it's difficult. We can't just integrate anything arbitrary. It might be very challenging to calculate it in closed form. However, when you place the mass over these delta functions, when we integrate it, what happens? First of all, it will break the integral, right? We only need to evaluate the function at these IID samples. Well, that's good news. Second, because of the linearity of the integral and this sum, we just need to basically evaluate the integral independently for each of the terms in this summation, right? Because the integral of x plus y, right? This integral of x plus integral of y, okay? You don't have to write them together. Now, the delta will break the integral. We evaluate the function, and we have this 1 over n, because we know we would need to normalize it. The probability needs to add up to 1. That's why we're doing this, okay? Otherwise, it will depend, right? The value of the integral will depend on how many examples you draw. We don't want that, right? You should get the, ideally, your intuition should say that probably that we should maybe get better answers if I have 1,000 IID samples rather than 100, right? But also, I should get roughly the same answer within some error bounds. The value of the integral shouldn't double because I'm drawing half of the samples or twice of the samples. So that's why we need to normalize it. So the trick that we did enables us to evaluate this expectation. Basically, that's the idea. And of course, you can apply it to any function. This method is a way to integrate, calculate expectation. Not specific to this framework. This is related to Monte Carlo integration. Now, the estimate of that integral is unbiased. That's very important. Meaning, in the limit, as you draw infinite number of samples, almost surely will converge to the true value of the integral. With probability of 1, that means definitely will converge to the true value. That's the law of large numbers. If you repeat something more often, it's more likely it gets closer to the true event, right? That's the law of large numbers in statistics. Now, why it's unbiased? Because when you write down the definition of the variance, which is the expected value of x squared for random variable minus mu squared. Remember that? Right? We had this before. So write down and define it to be this whatever variance you want to name it. Now, we have to assume this is bounded because otherwise it breaks down the framework, right? Assuming the posterior variance is bounded, then we can talk about sample variance. Because the examples are IID, right? All of them comes from the same distribution. Therefore, all of them, they have the same variance. Therefore, when you talk about the sample variance, you get this clean formula. This is the same sample mean variance idea we talked about in your homework. Right? There's a population. Sample is a subset of that, which behaves like the larger population when people do survey, right? So what's the average income of American, right? Don't know. There are 300 million. Do they call all of them? Probably not. Maybe they ask 1 million of them, try to spread it around as much as they can, different demographics and locations and all the variables experts know, right? And that's the sample, basically, estimate. Sample mean is the income, for example, they tell you, I don't know, what is it? Is it 20K? 60K? 100K? They tell you maybe it's 60K, but then what is the sample variance, right? What if the estimate is here, but the dispersion is, or the interval that these numbers come from is so large that in reality, if you take an example out, it's unlikely to be close to that mean. Because mean is the hypothetical situation, right? I always wondered who's average American. Then I realized one day, oh, that's not a real person. That's what when the statisticians talk about. It's not a real person. It's just a concept that does not exist in reality. That's the mean. In reality, could be somewhere here, right? Now, so it's important when this interval is large, it's less trustworthy, right? If it's small, it's better. Okay? Now, this is called sample variance. Sample variance is the standard deviation of, or variance of, the sample mean. And what happens when n goes to infinity, that means if you asked the entire population, right, every possible person who lives in America, then there is no variance for the sample mean, because that is the true average. So this concept is very important. The sample variance is the variance of sample mean, because sample mean is a representative of the entire population, not the population itself. So when it goes to infinity, this goes to 0. We nail down the mean exactly, which means it converges to the true value, right? That's why it's unbiased, following this sample variance of the mean. You had a question?
Yeah. Could you please go to the previous page?
Am I going too fast? A little bit?
What's the meaning of alpha script I over S?
The I, the question is, what is this I here, right? I'm using, so you remember the subscript was for time, right? I'm using superscript to track these random, IID random samples, the particles. So I have particle 1, particle 2, particle n. I need to track them. So in another sense, to give you more, basically, intuition, is that in Kalman filtering, we were tracking only one particle, a single hypothesis. You can think about this filter as essentially running a lot of Kalman filters, right? Roughly, not.
So why in the Pn function within the bracket, there is a subtraction between x0 to k minus.
So with this notation, I'm emphasizing that the mass of this probability is centered around these IID samples, right? Just matching the delta notation we had, delta. Yeah, you don't need to overthink it. You could write it the other way as well, right? Just emphasizing the mass is centered around these points, not everywhere else, okay?
Can you explain the left-hand side of this equation?
Who's talking?
It's from Zoom.
Oh, from Zoom. I thought it's future you talking to you. That's not the right question to ask. Okay, so let's hear the question on Zoom.
So can you explain more about the left-hand side of this equation? I'm a little confused about the notation, like in front of
Well, let
inside
me fix
this
the
parenthesis.
notation. You guys are very uncomfortable. How about this?
Yeah, it's better.
Very good. You're free to. Now I'm following standard notations from references that I give you, but I don't think that's important. So the posterior is over still your random variable, right? It's just placed over these random samples. Is that basically an answer to your concern?
Yeah, I guess.
Okay.
So on the right-hand side, the delta function is centered at random points. From
Each term is placed around one example, but we have delta of x minus x1 plus delta of x minus x2 plus delta of x minus xn, right?
Mm-hmm.
So we have n of them. If you integrate this empirical distribution, what will happen? If you integrate p of n, this will give you n, because if you integrate delta, it will give you 1. Now, I don't want that because the density should add up to 1. Right? One of the axioms of probability is that when you integrate, it should add up to 1. So I add a normalizing constant here to make sure it will add up to 1. Okay? Then we have, this is called an empirical estimate of this distribution. Okay? Now, you might not need to do this. Obviously, this is an approximation, right? But within this framework, this is a good idea to build our method, okay? Of course, we're losing something by discretizing the distribution.
So before you mentioned that the particle filter we can think of in the sense of doing a Kalman filter a bunch of times.
Mm-hmm.
So So does that mean that we should think of particles instead of point masses at certain locations with a certain weight? Are they point distributions?
Yes, they are an event, right? Each particle is, now the question is, should we assume each particle is basically a distribution? We consider a posterior that describes the entire sample, okay? When you're talking about individual particles, the evolution of that event, right, the way it rolls out as you collect data, you could imagine it as if you're running one column filter. That will not describe the entire set. It is just about that single particle, right? If you want to describe the entire sample, then you need to talk about, let's say you're tracking a mean and covariance, then you talk about a mixture of these little Gaussians. So you can build the posterior. So this posterior is much more powerful. It's describing all of these particles, right? We're not going to make it that complicated, but that's the idea in FastIslam. When they did particle filtering Islam, for landmarks, you're tracking them with EKF, and then for the robot, you're running a particle filter. You can combine them. But we won't do it today. We just about particle filtering.
Professor, I have one more question.
Is there another question?
Yes, this is from Zoom as well. Can I see the previous slide?
You would like to see the previous slide, okay?
In the blue that you've drawn, you have probability of x from 0 to k. Does that mean there are k probability distribution functions here?
No. The question is, when we write probability of x, well, yes and no. When you write the probability of x from time 0 to k, we mean their joint distribution, right? Of course, they have marginal distributions too, because you're saying that do we have k different densities? Yes, you can talk about their marginals, but I mean their joint density, right? It's the same as, same notation we used before. This will be their joint distribution. Okay? You can marginalize, then you will have k different densities. Okay, so let's continue. And the last point, if you're an estimation enthusiast and you like central limit theorem, you can show that if the variance is bounded in the limit, this random variable here, square root of n, times the error, basically, between estimate and the true value. In distribution, it will converge to this Gaussian distribution, zero mean with a true variance. So the central limit theorem holds here.
Just to make sure it's a function of I of f, just a constant.
Which one is constant?
I function of f.
This is the true value. I of f is the true value of this integral. Right? This is I of f. If you could truly evaluate it, if you could evaluate this integral given a function f and a density, posterior density p, what would you get, right? This I, right? That's just the value we get out of this integral.
Why is that I?
Well, because we can't calculate this in general, right? If we could, you can throw away everything, basically. But if you can't, you need an idea to integrate, right? So that's why we talk about this approximation. Okay?
The small n is like sampling n, like n points from a data set, right? So shouldn't n go to that, the number of like actual points instead of infinity? Like if you're taking n from, let's say, capital A, shouldn't n goes to A?
Let me understand your question. We're not sampling from data set. We're sampling from a true posterior that we assumed we know it, right?
Yeah, okay.
This is not about data set, or this is a hypothetical situation that we know the true posterior and we can draw samples. Then we are able to approximate this integral and evaluate it. And in the limit, as you draw more samples, it will converge to the true value. That's the takeaway, right? This much we can do right now. So you can write a loop in the computer, not very hard to code, draw samples. You have access to your function. We can evaluate this function, right? And we assume we can draw samples, then you're able to approximate this integral. Okay? So we can estimate any quantity. There is no limitation in what type of function we're dealing with.
I was wondering, is there a rule of, in general, how to know how many samples you need to collect before you can safely assume that it is, that your samples actually represent your integral?
No. So the question is there a rule? Tell me how many samples I should take? Well, that would be too good to be true. Right? And the answer is no. The more, the merrier. If we knew that, then why would we need engineers? Anybody could do it on the street. Your judgment is important, right? To set that number of samples. Not too low, it will become degenerate. Not too high, it might be overkill. Maybe with less samples, you're getting already good results, right? So it depends on a lot of things. Do you care in a length that you're estimating in kilometers, an error of the order of 1 centimeter? Probably not, right? So real problems usually give you more intuition what sort of thresholds you can choose, especially if they have physical meaning. It makes it super easy to judge. Now, a very important fact is that the rate of convergence is independent of the integrand dimension. It doesn't matter how high dimensional is this integral, your function. As long as you can draw some samples, you can evaluate the same, basically, averaging of your function evaluation. That's very important because any other numerical integration method, basically, the convergence rate will decrease as the dimension of the integrand increases. That's the curse of dimensionality. As the dimensionality of the space goes higher, a lot of methods basically become slower and slower. And that's a very big limitation in practice. Do you know any other numerical integration method? You might have seen some other methods, maybe? Quadrature, right? The Riemann integration, the simplest one, you have a bunch of rectangles, right? Now those rectangles, in 3D, they become cube. In n-dimensional, that's a hypergrid that you need to loop over. So you keep adding nested loops, right? That the complexity grows exponentially. So this method is not deterministic, it's based on random sampling. All right, that's all good and nice. What's the problem? you are all sold with the silly assumption that I made in the beginning. Yeah?
So I guess it's not probably what you're thinking about. To say it's probably very time inefficient.
Time inefficient. No, there's a bigger problem, much bigger problem.
We don't know the posterior distribution.
Right. We don't know the posterior. If we knew it, the problem basically would have been solved to begin with, right? So that's the problem. So if you know the posterior, you can draw a sample, you can evaluate it. But the problem is, of course, you don't know the posterior to begin with. So that's the problem we are facing with here. If you knew where your robot is exactly, why would you run a localization algorithm? You just know it, okay? So we need a new idea to bypass that problem. There are many methods for basically bypassing that, and we won't talk about all of them here. We talk about one of them in particular that is important to us for this sequential Monte Carlo method, and it's called importance sampling. Here's the idea. I do not know the posterior, therefore, even if I could, I cannot draw samples because I don't know it. Define a new distribution that we know it, anything that you know. Call it importance sampling distribution or proposal distribution. However, we need to make an assumption that if this is P, my proposal distribution's support, right, covers the true posterior. So we need that. Otherwise, if you work with this, basically the hypothesis that you will generate using this proposal distribution as a surrogate for the true posterior, it will never basically cover everything, right? That's the reason why we wanted to cover that. And their answer is that we don't know if it will cover in practice or not. Okay? Again, if you knew the posterior, there's a lot of things we could do. So another basically design choice or judgment that we need to make. Okay? So we need that. So when you read that the support of this pi should include support of p, that's the reason. Because when you generate hypothesis samples, then there is no chance to cover this area. And that's not good. That includes our possible operating point. So put it in the form of some equations. First of all, you remember this part. This was the integral we wanted to calculate, right? The expected value of the function with respect to the true posterior. Can I divide it by this, basically this integral here? Well, this adds up to 1, right? There's no problem adding that. And that might remind you some formula for center of mass and some sort of weighted averaging, right? And it is like that. Now, we propose to define a weight that is the ratio of true posterior over the proposal distribution. If you do that, then you can replace the true posterior with the weight times the proposal distribution, right? this is what we get. So that's the crazy line that you see in the beginning. It follows from this, right? Take the integral divided by 1, which is the sum over the posterior. Define a weight to be the ratio of true posterior over the proposal distribution, then substitute it into this equation, and that's what you get. So we have not done anything besides just manipulating terms. However, we know that we can approximate that integral. Now, f times w just is another function, right? And I know pi. I can draw samples from it. Using what we learned from that Monte Carlo approximation, now I can evaluate both of these integrals, which lead to basically in the numerator, it's the n sum over f times w, and the denominator is basically the sum of the weights as a function. On top of that, let's take this denominator and normalize all the weights, right? To make it cleaner, we're going to normalize all the weights, this w tilde, and we get this interesting equation. So it sounds like if I replace the true posterior with a proposal distribution, the uniform, basically, approximation will change to a weighted sum. And that weight depends on the proportion of the true posterior and the proposal distribution. This is interesting. But it's not sufficient for recursive state estimation. So we're going to continue. So the checkpoint here is that if I replace the true posterior with a distribution that I know, I can approximate the integral using weighted sum now. And these weights basically depend on the ratio of the true posterior and the proposal distribution. Still not good. We need to continue, okay? All right, so let's factor this proposal distribution with no approximation. This is basically chain rule of probability, right? If you have P of x and y given z, it's P of x given z times P of y given x and z, right? That's all I'm doing, first line. So this is x 0 to k minus 1 and xk. Basically, this is the joint distribution for these two variables. So we get probability of xk given everything else times the probability of the other one given everything else. Now the reason we drop zk, right? This is k minus 1. Because data is coming sequentially and the causal, right, effect in our models that we consider, we drop the future data. Now, let's do the same thing for the new probability at time step k minus 1. You get exactly the same thing. You keep repeating that. At some point, you reach to the prior, and you have factored successfully all these xj terms to be conditioned on the trajectory except that point j, right? Or basically up to that point, right? Up to the point j, time step j, and the data up to that point. So we can factor this distribution exactly. We are just using the chain rule of probability, right? We did not approximate anything. What about the weights? The weights were the distribution of the true posterior and the proposal distribution. We managed to factor pi like this. How about we factor the true posterior as well? Now, this is exactly equivalent of what we did in the upper part. P of xk What about this term? Now, you know from Bayes' rule that you can write this as and then you can make all those Markov assumptions, drop the redundancies based on the Markov assumption. This will give you what you see on the slide. Okay? So no magic. These are all follows from all the assumptions we talked about, the chain rule, Bayes' rule. But I do encourage you to go through it one time because it can be confusing. There are a lot of terms, and it can be intimidating. But they all follow from some basic manipulation of terms. So we can factor the posterior like that. And if you basically divide them, right, sounds like I can get a recursive formula that, because this first part, if you divide them, right, that's just the weight at time step k minus 1. The more interesting part I'm going to how about we basically drop this term and make it proportional? That's a very hard term to calculate. We have no idea how to do it. Okay? Well, what we know is a normalizing constant, right? It does not depend on x. So let's drop that, and instead of exactness, let's say the weight at time step k is proportional to the weight at time step k minus 1, which follows from this term here, 1 divided by this term 2, right? 1 divided by 2. And the more interesting part is that now the numerator here divided by this term here. That's what we get. All right, so now we have, it's got very messy, but we have a recursive formula for the weight. We needed that. Otherwise, there is no way forward. But we managed to turn the weight calculation recursively in the sense that if I know the previous weights, there are some terms that are familiar. These terms, what was this term? And what was this? I'm going to add a u here so you remember it, but it doesn't matter. We know these models. That's our likelihood. And that's the motion model, right? And of course, we know the proposal distribution. This is really nice. Now we know all the terms in this recursive formula. And if we start at time 0, we just need to initialize the weights, right? Sounds like now it will work. Because in the beginning, we initialize the weights maybe uniformly. That's what you did in your circular world with Bayes filter. I have no idea where to put the mass. Maybe let's just distribute it uniformly. Then next time, based on observations and motions and the proposal distribution, we can update the weight recursively in time. And then we will have the weights, and then we can evaluate that integral. Okay? So that's the idea of importance sampling, plus this recursive weight calculation. So the recursive calculation is actually called SIS. It's a sequential importance sampling. Importance sampling itself was not sequential. So this is called SIS, or sequential importance sampling. Well, I know it was a little of a headache. But I think it's very important to match that concept and intuition with these equations, because that's what you will implement.
It still is kind of confusing me because, like, I guess the reason why we went to this method was because we didn't know the actual distribution. So we said, okay, let's propose the distribution for it, but how do we know that proposal is representative?
Yeah, very good question is that we thought that we know that we don't know the true posterior, and then we said that let's propose a distribution. And then the question is, how do you know that's a good proposal, right? In general, we don't know. For a specific problem, the expert knowledge or domain knowledge can help us to choose a good proposal, which we will do it now for robotics, right? But keep in mind that when somebody from a statistics or math background is developing a method, they like to keep it as general as possible, right? This is us that we want to make it specific for ourselves. There are people in other fields making different design choices using the same methods. So that's why you see this generality. But of course, generic methods often don't work well for us. We need to adopt them in a way that we can specialize them for our application. And that's what we're going to do. Now, first simplification is that in filtering, we do not need to track the history. First thing to do, we delayed this simplification until now. That was without simplification. Let's drop the history using that Markov assumption that we had in the filtering and keep it just to be conditioned on the previous state by assuming that we have all the knowledge in the previous state. So that's the posterior, right? Do you recognize the posterior? Pi xk either. Well, we can write this as well. Right? So that's the posterior. We're going to make it even more, basically, special. The special case is that when the importance sampling distribution or the proposal distribution is the prior or the motion model. The motion model that we use for prediction in a more general context is called the prior, right? Because that helps you to basically predict where you are. Gives you a prior before you observe where you are. Imagine we set this distribution that's our design choice, right? We can choose anything. One of these particular choices is interesting. If you choose the motion model and just keep it to be your motion model, then what happens is that well, there's no, this was Z in general, but I'm choosing it to be my motion model, right? So if they are the same in the recursive weight formula that we calculated, then I can simplify these two. That's very nice. My recursive formula is now, it's really simple. That means that we'll evaluate your likelihood model, the sensor model, add the weight to the previous weight. Just rely on observations. But draw your samples from your motion model. It makes sense for the robot because if you have a model that describes the motion of your platform with some noise, you can generate different noise, maybe realizations, and then simulate how the robot might move forward. And that's a really good set of prior proposal, right? Given that you are here, and then maybe with some drift, you might end up here, or here, or here, or here, but not the other side of the room, right? For another particle, given that the particle is the other side of the room, same thing. It will move around that area. It won't move here if the proposal distribution is your motion model. Okay? So that particular, so it leads to two algorithms. If you don't make that simplification, that will give you SIS particle filter, sequential importance sampling particle filter. This is a generic particle filter. Basically, to simulate, you start with a set of state and weights. Now, if the state is, let's say, a 2D robot with orientation, X includes your 2D coordinates and orientation, right? That's your state vector. The weight is scalar. It's a weight for that particle. Initially, you start with maybe an empty set or uniform initialization. Sample from proposal distribution, update the weights, right? This is empty set for K, right? And then add the updated particles for all of them. And then you're done, okay? That's called SIS particle filter. So in 3 lines, that's the algorithm. What's wrong with it is that you start with a set of particles, and you keep evaluating weights, right? So you draw samples, you weight them. So each time, based on your previous particle, right? You draw a sample and you update that. So it will move. Based on your proposal distribution, the particle will move, and then you weight it based on this complicated formula. So what will happen is that as time increases, this distribution will become more and more skewed. At some point, it reduces to just one particle with non-zero weight after a few iterations. Why? Because if particles are spread around, and most of them are unlikely maybe, and they're moving around, right? This randomness in the behavior makes it very possible that a lot of times you get low weights, right? A sequence of low weights multiplication will basically reduce the weight to 0. And at some point, you will have basically one particle. You can simulate this. This will happen, and that's the degeneracy problem, okay? So basically, randomly moving a bunch of particles around and reweighting them, unless you can generate unlimited number of particles, will no good for us. This is known as a degeneracy problem. To fix the degeneracy problem, an idea was introduced that's called resampling. So resampling is an idea to fix this, which we will talk about it in a bit. For degeneracy, there is a measure. You can define an effective number of particles using this quantity, 1 over sum of the square of the weights. In two extreme cases, if all the particles in the beginning, right, they have uniform weights, right, you get 1 over sum of which is n over n squared, right? This will give you n. So if all the particles have the same weight, basically the effective number of particles is all of them. You want all of them. If the entire distribution mass is placed on single particle, which means all of them are 0 except one of them, the effective number of particles is 1. And that's what will happen. That's the two extreme cases of this basically formula will help you to monitor the degeneracy of the filter. All right. See, somebody is sleeping in the front row. We're done with degeneracy. We're going to talk about resampling. Are you awake? Sample impoverishment basically is a new problem, but we're not going to fix that. We just ignore it. So resampling reduces the effect of degeneracy. That's the idea. And the idea is pick the particles with higher weights and replicate them and get rid of particles with lower weights. This way, you can use a limited number of particles, a limited amount of resources to run the simulation for a much longer time. Because you get rid of unlikely hypotheses and reproduce more likely ones. Okay? Does that sound like a good idea?
I'm confused about why this method is useful, because if the weights, for example, in update step, some particles remain a weight 0, but at sometimes maybe they can be updated to a non-zero number. So why should we resample?
Well, if the weight, so the question is why this is a problem, even though the particle weight is almost 0, maybe I see a good observation suddenly and then I can come back, right? Can a particle come back? That's your question. Well, if the weight is roughly, let's say, 1 times 10 times minus 16, and you add a bunch of, I don't know, your weight is even really high, 10, right? Your updated weight will be something like this, right? You need way more than one good observation to come back, right? So one of them will survive because basically your filter should weight one of them higher, right? Because the filter is not weighting the particles in an absolute sense. It's relative to all other hypotheses. One of them will get higher weight based on the proposal. And then when they go lower weights for a couple of iterations, it's very difficult to recover from that.
So it means that one single particle dominates the,
Yes.
the distribution, and there is no chance for us to retrieve the true distribution.
Yes, there's no chance to recover, but the reason there's no chance, because there's no mechanism in the algorithm to recover. The algorithm is not trying to fix that. It's just propagating particles and then weighting them, right? There's nothing in the algorithm to deal with that problem. So now we want to augment the algorithm with some method to deal with that, and that's the resampling. Now these ideas are very, you can play with the code examples to replicate them. It's not difficult. So the resampling idea is good, but there's a fundamental problem, and that's the problem of loss of diversity. Because so basically if you start from a set of equally likely particles, right? And then we propagate them over time, and then re-weight them, right? Maybe this one has a lower weight. Now lower weight. Now we're saying that, well, these are not very likely. I'm just going to end them here, right? Now I'm going to make maybe 2 of this guy, 1 of this guy, 2 of this guy. And then let's say we get a fresh start equally weighted, right? Then you do it again. Maybe this time, this is not very likely. Maybe very likely, maybe not likely. And then you say, I'm going to kill these 2 as well, these 3. So now this should give me what's the problem? By keep resampling, at some point, we're tracking a fixed number of particles, right? Here, 5. At some point, all the hypotheses are originated from one parent. That's obviously against the idea of running multiple alternative hypotheses so that we can model multimodal distribution. So that's the fundamental problem that is introduced by resampling and called sample impoverishment. So there are 2 problems, right? Degeneracy introduced by SIS and sample impoverishment introduced by resampling, but we're not going to fix that. It's good tuning, we'll make it work, but this problem is there.
So can we increase the number of samples? Let's say initially low samples, but as we go on increasing, so we can increase the number of samples. So the total time will be less initially. If we resample all the samples.
The question is, can we make the number of particles adaptive? That means maybe initially more particles, as you move forward less, or vice versa. Yes, there are many variations of the algorithms, including your textbook. You can use KL divergence and some other methods to adapt the number of particles. Probably in the beginning you want more particles that you're trying to bootstrap or initialize the filter, right? Once you are around the most likely hypothesis, maybe you just need a smaller number of samples to track. You can. We're not talking here about different variants of the algorithm, right? Because once you know the core algorithm, you can make a lot of, it's easy to understand the different variations of it. But that was a good idea, and our papers published on that idea. Around 2003. So you're very unfortunate that that idea is published already. Okay, so a generic particle filter with resampling will become like this. Start with a set of particle, choose a basically resampling threshold. Empirically, I don't know, 1 n over 3 or n over 5, maybe it's a good number. Draw a sample from proposal distribution, update the weights, normalize your weights, add that particle to the set at time step k, calculate the measure of degeneracy. If the measure of degeneracy is less than that threshold, which was n over 3, run resampling. Get rid of some particles, replicate some of them. After resampling, all the weights are also normalized. It's a fresh start, they're uniform. So this way, we can always track set of more likely particles. Now, it's a very, basically, can't find a good word, but you need to be careful because too much resampling will make the filter again degenerate, right? But if you don't do it at all, it makes it degenerate. You need to find a sweet spot for your problem by tuning. For robotics, that's what we're going to do. So maybe this is what we want to remember, right? So the previous one is important because you read some papers, they're proposing something more complicated, maybe using sensor models and other ideas, right? But first time when you want to implement for your problem a particle filter, probably you want to try this. The difference is that draw samples from your motion model and update the weights by just multiplying them by your likelihood. So unlike Kalman filtering, when we had some algebraic equations to update basically the posterior parameters, right? Mean and covariance. Here we literally evaluate that likelihood that, let's say, is Gaussian, right? To get a value of that PDF and multiply it by the weight. So the posterior is characterized by a histogram, and these are with these weights. You can visualize it. At every step, you can visualize a histogram, right? And these weights, maybe they show you something like this, right? When you debug your algorithm, it's a good idea to visualize the histogram each time, monitor it as you tune it. Using the weights. These. So resampling eliminates particles with low weights and multiplies particles with high weights. The particles with high weights are selected many times, and that will lead to the loss of diversity, which is the loss of alternative hypothesis in the filter. Depending how complicated and nonlinear your problem is, that can cause a serious problem. And if it's not causing a serious problem, this loss of hypothesis, maybe you could solve it with the Kalman filter already, right? That's a sign that maybe it's not that nonlinear. So this is a resampling algorithm. It's called low variance. I just covered a basic idea that you see here. So you basically start with calculating the cumulative sum of all the weights, right? You enter the algorithm, get all the weights, add them up in a cumulative way, right? this will give you this cumulative distribution function, CDF. Okay? So they will get this W, right? C. And then this is from 0 to 1. This is the CDF, right? And you get something like, yeah, 1, 2, all the way to n. And then you get some weights like this, depending how much of the mass is located on that particular particle, right? It will occupy some of this CDF. So this algorithm is using just one random number and systematically replicates particles with higher weights. There are uniform number between 0 and 1 over n because you have n particles. That's the uniform distribution over individual particles. Then for all the particles, try to traverse this CDF with that 1n fraction at a time. First time, this is 0 because I equals 1, right? So we're working with whatever random number we got here. So if U is so we're processing particle J, right? So if U is bigger than the weight of that particle, we pass, right? If that random number is bigger than the cumulative weight of that particle, we pass. Until we find a particle here, let's say here, right? Basically here, that the weight, maybe you are here now, right? Until the weight is higher than this variable. So first time, what it means that if the particle's weight is less than that uniform, ignore it, right? Ignore all the particles until you find a particle that cumulatively is above that uniform initially, right? And when you do find that particle, replace particle I with J, right? And set the weight of that particle to uniform. Next time, increment U, basically with so basically 1 over n, right? But because it's using the initial random number, you want to work with that one random number. You don't want it to be exactly 1 over n, right? So U is R plus I minus 1 over n. Now you increase it, next time you repeat that. When you repeat this, next time you're somewhere here maybe, right? And maybe you ignore this particle here and here, and now you want to replicate this 10th particle. So what happens is that as this resampling traversing this CDF, some of the particles that have low weight, they make a little change cumulatively with respect to the previous index, right? Therefore, when you increment with 1 over n, it will ignore them because that 1 over n is bigger than a small increase in the cumulative weight. That's the idea. And in this process, it could be the case that this while loop is true, basically false, for several times, right? So what happens maybe for particle 3, 4, and 5, you just replicate particle 3. That's what will happen, okay? So that's the idea of low variance resampling. it is usually helpful to write it. If you have time, we can go over it. You can write it with maybe 5 particles and see how it goes. By the way, you have it in my previous lectures that I shared. Somebody asked for previous year's recording, but the number of watches was 0. That was very sad. It was good for me to see what I said last year. Thanks for whoever asked. Well, let's look at the examples. So let's look at the same target tracking example. We have a nonlinear model for the measurement, and the motion model is still linear because we don't know anything about the target. We assume the same previous position from the target at time step k minus 1 plus some noise. And we assume basically WK is a Gaussian with 0 mean and covariance QK that you see here. And this one is also a normal distribution with 0 mean and covariance R. So this is the variance for the range measurement, and this is for bearing. Bearing is the relative angle to the sensor, to the y-axis here. So we run that particle filter, which is called SIR. That particle filter that for robotics we covered is called SIR, sample importance resampling. You sample for a motion model, you update the importance weights using the likelihood of sensor model, and then you do resampling. So the cycle is sample importance resampling. We don't want to resample every time, so we added a threshold to only resample when the filter is becoming degenerate, in the sense that weights are very low. The mass is becoming concentrated on one particle. So you can see that it's a filter, of course. There are some jitters, but you can solve the same problem. Now, you're probably bored at this time with this example. So let's also estimate the velocity of the target. This is a good practice for you to go and do it and change the previous column filters, try to estimate the velocity as well. You need to augment your state with the target velocity for x and y. Now, I'm assuming a constant velocity motion model for the target. I'm assuming that basically xk one is xk minus 1. No, wait. V is the velocity times delta t, right? The constant velocity model, it says that your velocity over time, delta t, is constant. I see no surprise. That's good. That's the assumption. Previously, it was constant position assumption, right? I was assuming the target is not moving over time delta t. I'm moving it one derivative higher. I'm assuming that velocity is not changing, which is a better assumption, right? You could go one more higher and say, well, constant acceleration assumption maybe. Then you need to integrate this twice. Which if you have IMU, then you can do that. On the object that is moving, if you can measure it, then the input is the acceleration, and you can include a better model here for velocity integration. So in any case, when you write this in a matrix form, now your discrete time system matrix is like this, which is identity times position, right, plus delta t times the velocity, okay? So the state is now not just position. I'm abusing the notation using x again, but I think you get it, you get the idea. I could use p, maybe. And x is p and v. So we're using the same data, I want to estimate the velocity as well. And we can do it. So now we track the target. We also estimate the velocity for each coordinates. How do you know the velocity is correct? Can we just add unlimited variables and see what happens?
But if you just like take the first derivative of the actual position and take the result of x1,
That's a good idea. You're saying that, well, how about we numerically, maybe we take the derivative of this plot, right? See if it matches that. And it should, because we integrated that velocity to get position, right? So that's a good way to check. Well, it is correct because the position is correct, right? However, this one is fine, but in general, when you augment your system, right, you need to check the observability to make sure with the same amount of information, measurements, you can estimate more variables. But position and velocity are very natural to include always, right? So you have my code as usual for MATLAB and Python. And we can summarize. So we learned a new filter today. It's based on random sampling. It's called particle filter. I bothered you with some of the derivations in case you're interested. But the outcome was that algorithm, SIR, particle filter. Now, we want to use this for robot localization, right? Now that we learned this filter, in future lectures, we will use this algorithm to solve the robot localization problem. It can deal with non-Gaussian online estimation problems. It can deal with global uncertainty. Global uncertainty means, in this room, again, you want to localize. You have no idea where the robot is located initially or at some point in time. That's the kidnapped robot problem. These algorithms are very general. You can tackle a very broad range of problems, not just robotics and localization. Now, the price to pay is the inefficiency in some application domains. If your state is high dimensional and you need to draw samples, you need more hypotheses because high dimensional spaces are very empty. If you have 20 dimensions and now you're drawing random samples, in each direction, you can basically move in an infinite number of ways, right, if it's continuous. So you need more samples, and that might become inefficient given that we don't track infinite number of hypotheses, okay? But when you can use it, it works very well. So that's all for today. The related readings are chapter 4 of probabilistic robotics. It talks about non-parametric filters. By the way, this is a non-parametric filter, as opposed to the parametric filter, such as Kalman filters. Can anybody say why it's non-parametric?
particles that you're trying to...
That's correct. There's no parameter to model the posterior. We just track a bunch of weights, a statistical information relationship for the posterior. So it is non-parametric. There is a statistical relationship that models input-output. So chapter 4, and this chapter 1 from one of the books that I basically shared with you. This is one of my favorites. It's really good to read. Chapter 1 talks about the sequential Monte Carlo in practice. So that's it for today, and let's see if you have questions.